For topic two, we're going to talk about the dot product and magnitude involving vectors with three components. We talked about this a little bit in 10.4, so this isn't completely brand new. I just kind of threw it at you in 10.4, so I'm going to throw it at you again. So kind of envision this situation. We're used to the world of two dimensions, where we have an x-axis and we have a y-axis, but now we need to have something called the z-axis. Okay? So we have these two vectors, but the vectors are going to have three components. They're going to have a horizontal, vertical, and this third component, okay? So we have vector v, which is a sub 1 times I plus b sub 1 times j plus c sub 1 times k. And then we have vector w, which is a sub 2 times I plus b sub 2 times j plus c sub 2 times k. I, j, and k are just unit vectors, and they basically just give us a direction. So the vector I gives us a direction along x, the vector j gives us a direction along y, and the vector k gives us a direction along z. So let's say this is our x-axis, our y-axis, and our z-axis, okay? So we could say that I is a unit vector in the x direction, okay? We can say that j is a unit vector in the y direction. And then we can say that k is a unit vector in the z direction. So these vectors, they're just unit vectors. So that means they're one unit in each direction. They literally just give us direction. A, B, and C, A sub 1, A sub 2, A sub 1, B sub 1, C sub 1, and A sub 2, B sub 2, C sub 2, they tell us how far in each direction we need to go, okay? So these are vectors in three components. They're just kind of like a three-dimensional situation, okay? So we don't really have anything too scary to deal with. We already talked about adding and subtracting vectors with three components. We've already found magnitude of vectors with three components. Now we're going to find the dot product of vectors that have three components. So the only difference is you're going to take your A components and multiply those. You are going to take your B components and multiply those. And then you are going to take your C components and multiply those, and then add each of those products up. And that's your dot product for vectors with three components. Magnitude, nothing scary. You're going to take the square root of the A component squared plus the B component squared plus the C component squared. And then what's really cool about this, and we'll prove it in just a bit, but the magnitude of the vector v is the same thing as the square root of v dot v. The magnitude of vector w is the same thing as the square root of w dot w. So that's a cool thing we'll show in just a bit, okay? Now, remember the result of a dot product is always a real number, and the same is true with the magnitude, okay? So let's look at some examples, all right? So luckily, we have our vectors in, we just have the position vectors. They're not in component form, which again, I've told you this several times. I think the I's and the J's, they just get so like busy and it's just kind of hard to see. So we have the vector V is 2, comma, negative 3, comma 6. So this is our how far we're going in the X direction, how far we're going in the Y direction, and then how far we would be going in the Z direction, and ditto down here. Okay, so it's just how far you're going in those directions. Okay, now if we want to find the dot product, it's no big deal. We just multiply the A components, the B components, the C components, and then add them. Okay, so let's practice. Let's do V dot W. Okay, so remember, we want A sub 1 times A sub 2. So that would be 2 times 5. We want b sub 1 times b sub 2, so that's negative 3 times 3. And then we want c sub 1 and c sub 2. So 6 times what is the other? Negative 1. So that's going to be 10 minus 9 minus 6. Well, 10 minus 9 is 1. 1 minus 6 is negative 5. So let me write this officially. So we would say the dot product here is negative 5. Okay. Now we already know that this is commutative. Okay. We already know that the dot product is commutative. So if I take v dot w, it is the same thing as w dot v. So we can just come over here. I would allow this anyway. We can say that dot product is commutative. So we can say v dot w equals w dot v. We already know v dot w, so we can just say this is -5. Okay, we don't really have to do any work here. Okay, now you have to be able to justify something like that for sure. Okay, and we can justify it by saying, hey, the dot product's commutative. We already know v dot w, so bammo. Bammo, whammo, here we get it. Now, if you want to go through and do the work to prove this is true, absolutely you can. Okay. Now, v dot v. Okay. So v dot v, we need to, I want to make sure I can still see my little vectors so I don't forget the components. So v dot v, I'm basically going to take my a component and square it, my b component and square it, my c component and square it. Okay. And we know this because we practiced this basically with something else before, but it's true. So if you, I keep forgetting to write out what I'm doing. So v dot v, okay, we want to take our a components and square them, our b components and square them, our c components and square them. So this is going to be 2 times 2, or 2 squared, plus -3 times -3, or -3 squared, and then 6 times 6, or 6 squared. So we're going to get 4 plus 9 plus 36. So let's see here. 4 plus 36 is 40, plus 9 is 49. So we can say v dot v is 49. And then w dot w, same thing. We can just take the a component and square it, the b component and square it, and then the c component and square it. So we would get 5 times 5, or if you want 5 squared, plus 3 times 3, plus -1 times -1. So we're going to get 25 plus 9 plus 1. Well, 9 plus 1 is 10. 10 plus 25 is 35. So we get that the w dot w, that dot product, is 35. Okay. And then let's practice finding the magnitude of something with 3 components. So the magnitude, remember, is the square root of a squared plus b squared plus c squared. So I would get 2 squared plus -3 squared plus 6 squared. So let's see here. We're going to get 2 squared is 4, 3 squared is 9, 6 squared is 36. Well, golly, that looks awfully familiar. So we get the square root of, I need to scroll up just a tiny bit more. We get the square root of 49, or just 7. So we can say the magnitude of V is 7. And in a little bit, we're going to look at this right here. So if we look at V dot V, we get 49. Okay. If we look at the magnitude of V, we get 7. There's a connection between those two. So if we take the magnitude and square it, we get V dot V. Okay. That's going to be really cool in just a minute. Okay. Now, finally, we want to find the magnitude of W. So remember, this is going to be the square root of the A component squared, the B component squared, the C component squared. Add them up, take the square root. Okay. So we are going to get 5 squared plus 3 squared plus -1 squared. So that's going to be 25 plus 9 plus 1. Well, dadgum, that looks real familiar too. All right, if we take 9 plus 1, that's 10, plus 25 is 35, so we get the square root of 35. So that is the magnitude of W. And again, take a little peek here. If we take the magnitude and square it, we get W dot W, okay? So that's going to be, I don't want to say it's going to be powerful, but you're going to see it again, okay? So that might be the next example. There, well, let me scroll. Okay. Yeah, so another dot product property is exactly what I just told you. So let V be some vector, okay? And it's going to be some vector. When you have this weird R symbol, so it's like a double backed R, it stands for the real numbers. It's just saying some like vector with two components, okay? So we're in the XY world. So like think two dimensions, okay? So if you have some vector v, then we can say v dot v equals the magnitude square. And we're here to prove it, okay? So for example 3, it says, given the property above, prove the following. Okay, so we want to prove that v dot v is equal to the magnitude of v squared, okay? So remember, when you're proving something, you want to work kind of exclusively on one side. However, I am going to go off to the side here, and we're just going to think about something. So when we deal with the magnitude, and remember, you can do the magnitude with single magnitude bars or double. Doesn't matter. All right, when you're thinking of the magnitude of something, we want the square root of the different components squared and then added. So we want the square root of the sum of the components squared, okay? So I would need a squared plus b squared. And I know I'm just dealing with two components because here we were given a vector that just had components a and b, okay? So that's interesting. So that's just the magnitude. But let's think, what if I took the magnitude and I squared it? Well, that would mean I would need to take the magnitude and square it, right? So if we were to simplify this, we would get that the magnitude squared is just equal to a squared plus b squared. So keep that in mind. Just sort of hold that thought. All right. So we're going to come over here and we want to prove that the left-hand side really does equal the right-hand side. So we're going to make this our goal. Okay. So working with just v dot v, how do we get this? Okay. Well, if we're dealing with v dot v, please keep in mind that v is the vector, or we have the position vector AV. Okay. So if we're going to do the dot product here, we need to take the A components. Okay. So the A components would be just A times A. We want to add the B components, so B times B. So that would be A squared plus B squared. So I need to find another way that I could write the equivalent, like an equivalent statement to this, but that would also equal the magnitude squared, because this is looking very magnitude-ish, right? We've got the A squared, the B squared. So if I take the square root of it, that doesn't do it because that's not equal. But if I take the square root and then I square it, that is equal to the magnitude squared, because essentially I just get a squared plus b squared when I do that. So the square root of a squared plus b squared squared is just a squared plus b squared. So we have an equivalent statement here, okay? So we can now officially say, well, hey, we did it. This is equal to the magnitude squared. So we can now say, hey, the magnitude squared equals the magnitude squared. We're done. So consider it proven. Okay. So it's just a cool thing that happens. It's nice. So if you're dealing with a situation where you know the magnitude, you can figure out the dot product pretty easily. If you know the dot product, you can find the magnitude pretty easily. Okay. So that's all. It's just a fun little connection. It's easy to prove, so why not prove it? Okay. In the next video, we're going to talk about the angle that is between two vectors. So like an angle that two vectors can form. Okay.